Hello, my name is Dher Mahmood and this is my presentation for ECE561 final project. So my project is about integrating flip and write with frequent value locality architectures for enhancing writing durability of PCM. So today I'm going to talk about the motivation and challenges of the emerging technology of PCM. I'm going to talk about the technology of PCM and the architectures that are used to enhance the writing endurance of the PCM, like the flip and write and the frequent value, and their implementation using Gem5. And then I'm gonna present some of the results that I got by running the simulation in the implementation. And then I'm gonna present my conclusions and some of the future work that I would have done if I had more time. And then the final slide will be references. Um, so the first thing I'm going to talk about is the emerging technology of the PCM. So the motivation for using PCM instead of DRAM is that it's non-volatile, it's scalable, it has high density, so we can um, put more bits in the same area, and it has fast reading speed. But the challenges of PCM is that its writing speed is very slow, and energy consumption is very high, and it wear out very quickly, so its lifespan is very short. So the PCM, which stands for phase change memory, is made of phase change material, which has two states, and each state is used to store different bit. So we have two states, the amorphous state and crystalline state. The amorphous state is used to store 0 and crystalline state is used to store 1. And the transition between the state is done by heating. And heating is done by applying current to the material. So if you look at the figure below, we can notice that if we apply the high current for a short period of time, we can achieve the reset state. If we apply somewhat lower current, but for a longer period of time, then we can achieve the set state. And for reading, we can notice that we need a very small current for a very short time. So we can notice that reading is very fast and very energy efficient, unlike writing. So that's why we're focusing on improving writing. So the first technique that we're going to use for improving writing is the flip and write. And the flip and write is basically a bit level writing enhancement technique, and it's very simple and deterministic, meaning that we can use a mathematical equation to predict how many bits we're going to save and not write to the memory by using this technique. So the basic idea of flip and write is that if we have a byte or word that we want to write to the memory, then we can read the old byte stored at the same location and then compare the two bytes bit by bit and only store the different bits. And this is actually called data comparison writing. And the flip and write improve upon the data comparison writing by using the Hamming distance. So if the Hamming distance is higher than half the byte size or the data size, then we're going to flip the data and reduce the Hamming distance to smaller than the half size. And then we're going to use an extra bit called the flip bit to indicate whether the data stored at the memory is flipped or not. The next technique that we're going to use is the frequent value. And the frequent value is basically a byte level writing enhancement technique. And many researchers show that the three most written values to memory comprises 50% of all writings. So for this purpose, in order to take advantage of the frequent values, we introduce the frequent value cache, the FVC. And so the frequent values are written to the cache in encoded format. And we're going to save log 2 frequent values. So if we have frequent value of size 8 or 16, then we're going to store 3 or 4 bits instead. And it can easily be integrated with the flip and write, but then the trade-off is between storage and storage overheating lifespan. So because we're adding cache, then we're going to use more storage, but we may achieve higher lifespan. So the implementation of those two techniques is done by using Gem5. So Gem5 is open source computer architecture simulator, and it's mostly done by using C++, Python, and Ruby. and everything in Gem5 is object-oriented. So the first thing that I did in Gem5 was introducing a class called PCM, and I also added an option for choosing this memory. Then in the abstract memory file, which is located in the build alpha folders, I modified the access function within that file to introduce the flip and write and the frequent value architectures. And then the simulation result is read from the m5 out stats.txt file. And there's an entry in that file called number of bytes written to this memory, and I'm reading this value as a result. But actually, this value represents the number of bits written to memory and not number of bytes, because I modified the code to calculate the number of bits in flip and write and in frequent value as well. So the first application that I use in this implementation is the radix, which is taken from the Splash2 benchmark. So the first column, the original, represents the number of bits written to memory without introducing any improvement to the writing architecture that is implemented in the Gem5. So we have about 12,000 bits written to the memory in the original scheme, and then after I introduced the DCW, the data comparison writing, we can notice that the number of bits written to the memory drops very dramatically to below 2,000, which is a very good improvement. And then the flip and write improve more upon that. And then the frequent value provide a good improvement over the original, but still not as good as the DCW or the flip and write. But if we notice that if we combine the flip and write and the frequent value, then we are achieving a much lower number of bits written to memory as compared to all the other techniques. So we obtain the same results by using another application, the FFT application, which is also taken from Splash2, and we see that the trend is almost the same as the radix. Then the other application is the LU, which is also taken from Splash2. But here we notice that the DCW, flip and write, and frequent value are almost the same. They're giving us the same improvement upon the original. But then the combined is much better than each one of them. So basically we can achieve a good improvement by combining the two architectures of flip and write and frequent value for some applications. So what I concluded from doing this project is that PCM is an emerging memory technology that promises to replace DRAM, and PCM has some disadvantages that has to be addressed before it can replace DRAM. Most of these disadvantages are related to writing, like the writing energy, writing speed, and the WIRA. The flip and write and the frequent value are two memory enhancement techniques, and integrating these two techniques can further enhance the memory writing. And the results show that the technique reduced the two techniques combined reduce the number of bits written by 57% compared to flip and write if it was to be implemented by itself, and then 88% compared to frequent value. So the future work, I would have tried more applications from different benchmarks like Spec 2000 or Spec 2006, and study the energy consumption of writing operation after applying the proposed technique. I would have also studied the effect of proposed technique on reading speed, memory overhead, and other aspects of the system. And I would have further enhanced the frequent value by rotating the encoded bits stored in the memory to ease the pressure on certain bit locations. And here are the references that I used for this project, and thank you very much for listening.